Hello everybody and welcome to my math channel, the Sage of the Six Maths. My name is Bogdan and I'm just a local math tutor here in Strathroy, Ontario. I've decided to start just a small little YouTube channel mostly for my students so they can have access to some of this information and I can do some extra questions for them when we don't have time during the tutoring sessions, okay? So, without further ado, let's get started on the question here, okay? So here we have a rational function and we are asked to evaluate the limits at certain points, okay? So there's two approaches you can take. Either you take these limits, take these values for x, you plug them in and you kind of see where it takes you, or we can take more of a graphical approach. Try and draw the graph of this function and look at it to try and evaluate these limits. I'm going to take the graphical approach and show you guys what to do that way. So, first thing we need to do is we need to factor the top and the bottom to see, we're looking for vertical asymptotes, horizontal asymptotes, holes in the graph, all these different clues that we can use to draw the graph, right? Okay. Factoring the top part, we see we have a difference of squares, so it's going to be 3x plus 2 and 3x minus 2 over here. Factoring the bottom part, we're going to have 3x minus 2 and 4x plus 5. We see that the 3x minus 2 terms are common on the top and the bottom. Those can cancel out, which means there's a hole. So I'm going to take that, I'm going to set it equal to 0, so my negative 2 goes over to the other side, divide through by 3, we're going to have a hole at 2 over 3. Okay? I'm going to put that up here, just to give myself a little reminder that there's a hole there, okay? Now we're going to write a simplified form of our function, which is going to be 3x plus 2 and 4x plus 5, the two things that are left after canceling out the 3x minus 2 terms. To get the vertical asymptote, we're going to have to set the bottom, or the denominator, equal to 0. Okay, setting this equal to 0, the 5 moves over to the other side, becoming negative, dividing through by 4, You're going to have x equals 5 over 4 as your vertical asymptote, and then the horizontal asymptote, if we remember our rules for the horizontal asymptotes, if the degree of the numerator is the same as the degree in the denominator, your horizontal asymptote is determined by the leading coefficients. So the 3 and the 4. Y is equal to 3 over 4, that's going to be our horizontal asymptote. Drawing our graph here, I just put our asymptotes here, horizontal and vertical there. And another quick thing I want to do before graphing it, just another quick clue that I can grab here without doing a whole lot more work. I can put in 0 for x. Putting in 0 for x, these two terms are going to disappear at the front. I'm just going to be left with 2 over 5. So that's a quick point to sort of help me graph this out. I already put the point down right here just to save a little bit of time there. Another thing we want to do is I want to evaluate the limits here as they approach positive infinity, as x approaches positive infinity, and as x approaches negative infinity. Well, we know that we have these two asymptotes, so the end behaviors are actually going to be determined by these asymptotes. As x gets bigger and bigger, we're probably, because we have this point here, we know sort of the general shape of it. It's going to come from this side, right? I'm going to be going to that horizontal asymptote, the 3 over 4, right? On this side. And we're going to come around and we're going to come down here. Okay? So that's going to be our 3 over 4. Our vertical, our limit as x approaches negative infinity, well, that's going to be going this way. So we know that there's going to be a part over here on the bottom and another part coming over here at the top. If we remember what from our rational functions from previous years, this is sort of the general shape, right? So this is going to be 3 over 4. And if we want to confirm that the graph is actually on this side, you can plug in a point. Say you plug in negative 2 into your function, you'll see that it'll give you some y value in this area to confirm that it is actually over there. Okay, so this one is going to go this way, and and it'll look something like this. Okay. Don't forget our hole, okay? We have a hole at x equals 2 over 3. Where is x equal to 2 over 3? Well, if this is my 1, oh, hold on. Let's put it over here. This is our 1 hash mark here, 2/3 of the way there. That's going to be somewhere over here, okay? So I'm going to make a quick little, I'm going to draw that one in orange so that we can see our hole there, okay? So the function doesn't actually exist at that point, but it continues afterwards, okay? Limit number 1, the limit as x approaches 2 over 3 of our function. Well, we just figured out that when x is equal to 2 over 3, we have a hole there, right? But the definition of a limit is that the function, the limit exists if the limit when it approaches from the left side is the same as the limit when it approaches from the right-hand side. And this is going to be a value. So the limit does actually exist. The function doesn't exist at that point, but the limit exists because that value is going to be the same at that point. We can't plug this point into here, into this part, because if we do, we're going to be dividing by 0, so we can't do that. We got to plug it into the simplified form over here. So we're going to go ahead and do that. We're going to go 3 multiplied by 2 over 3 plus 2, and then on the bottom we have 4 multiplied by 2 over 3 plus 5. On the top, my 3's will cancel out, right? I just have 2 plus 2. That's just going to be 4. On the bottom, we have 4 times 2, which is 8 divided by 3, right? So we have 8 over 3 plus 5 over 3. Sorry, we have 8 over 3 plus 5 over 3 plus 5. Well, that's going to be 8 over 3. Let's just do that on the bottom here really quick, okay? 8 over 3 plus 15 over 3. Finding the common denominator, right? That's going to be 23 over 3. Yep. And so we have 23 over 3 on the bottom. So that's going to be 4 divided by 23 over 3, which is the same as saying 4 multiplied by 3 over 23. So 12 over 23 is going to be our value, okay? 12 over 23. Okay, just like that. And if we look at our graph, 12 over 23, that's about halfway up here. That looks about right where our hole is. So our drawing, even though it's a little bit of a rough sketch, it looks fairly accurate, okay? So here, the limit as x approaches negative 5 over 4 of f of x. Well, negative 5 over 4 is our horizontal asymptote. So let's see. As x approaches negative 5 over 4, same rule that we used up here. The limit has to be the same coming from the right side as it is from the left side. Well, if we come in from the right side and we go to negative 5 over 4, from the right side I have negative infinity. From the left side I have positive infinity. So they're different from coming from the left and the right, which means the limit does not exist, okay? Does not exist. Just like that, okay? The limit as x is approaching 0. Well, the limit as x approaches 0, let's see. X approaching 0 from the left side, we got a value. We got a value from there too. Oh, wait a minute. We already calculated that value right up here. That's one of the points we used to help us draw our graph in the first place. So since we already did it up here, I'm just going to go ahead and write, is it the same from the left side as it is from the right side? Yes, it is. 2 over 5, right? Plugging it into here, the 0, we have 2 over 5. And yeah, that's it right there. Hope you enjoyed it, and have a good one.